Hello and welcome to Toddcast number 13, covering resonance again. So this is resonance part two. Toddcast 12 was also resonance. This particular time, what I want to do is go into more like details about what makes a stable resonance structure, why one will be considered more favorable than the other, and ultimately look at what's called the major and minor contributors to a resonance hybrid. And hopefully it just picks up where things left off. Again, this is a major topic in organic chemistry. So with no further ado, we'll go ahead and get going. So resonance contributors refer to any resonance structures of the same overall molecule that go in to make the resonance hybrid. So early on, a lot of classes will say count the number of resonance structures. More resonance structures means more stable. And while this is typically true, almost always true, I like to teach it a little bit differently. So I'm going to go about it in kind of a more advanced way. It's a way that people eventually discover down the road when they look at chemical reactivity, how it affects it. So emphasized last time that lone pairs can become pi bonds and pi bonds can become lone pairs, meaning lone pairs will donate in, generally speaking, and pi bonds will withdraw out, generally speaking. So if I have this structure here, and X and Y represent any two atoms, there's not like misspelled xenon and misspelled yttrium. It's just two random elements. This pi bond here can break. And again, we draw resonance arrows starting from the center of the electrons in a bond being lost and draw the arrow to the atom to which they're going. And then lone pairs become pi bonds. So lone pair, and I could have picked any one. Arrow starts from the lone pair and goes to the center of the bond where the pi bond will be made. Okay, so that's convention of how we draw it, but I want to emphasize something. Pi bonds, if they break, and that's typically what we do, means they pull electron density away from the center. So I'm going to refer to that as an EWG, an electron withdrawing group. Conversely, the lone pairs, they donate in. So lone pairs donate in. So they're considered a electron donating group. So how this impacts things? Well, if we go back to simple acid-base chemistry, let's say acid is H plus and base is OH minus, take the simplest perspective. That means acids, acidic compounds, typically will have a more cationic or plus nature to them, and basic compounds will have, like OH minus, a more negative compound. And it makes sense because bases are lone pair donors. So lone pair donating is best done with a negative, and acids are electron pair acceptors. Electrons will want to go somewhere it's positive, so positive makes sense. So generally speaking, an electron withdrawing group will help make something more positive because you're taking electrons away. So it will increase the acidity of a compound. And then lone pairs that donate in, that's kind of what a base does, add electron pair in, that will help make the rest of the compound more basic. So we're going to use this to predict behavior in terms of basicity, acidity, and then as we get further along in chemistry, Lewis acid and Lewis base nature, which is going to be known as nucleophilicity, how well it donates a lone pair is Lewis base definition, but it's also what a nucleophile does. And then Lewis acids, they're electron pair acceptors. That's what electrophiles are going to be. So this doesn't mean much now, but it will. Electron donating groups donate in, electron withdrawing groups pull away. In general, electron withdrawing groups are comprised of pi bonds. Lone pairs make up electron donating groups. Okay, so I'm going to erase my writing and let the computer do its thing. So again, same story. This bond is breaking, so the electrons are going from the bond, the pi bond, to the atom where they're going to finish. Notice electron withdrawing group because it's pulling electron density away from the rest of the molecule. And pi bonds are electron withdrawing. Pi bonds turning into a lone pair is pulling electron density away. A lone pair going in to form the pi bond. So starting from lone pair, the arrow will curve around and go to the bond where the pi bond is forming. So lone pairs are going to be found in electron donating groups. So hang on to these terms, they become critical as we go. So in the end, we get this other resonance contributor. Okay, now we're going to start ranking how important a resonance contributor may be. And so there's a series of rules we follow, but the first and most important one is, does everything have a complete octet excluding H? So in this case, this X had a lone pair, lone pair, lone pair, and part of a bond. So 1, 2, 3, 4 electron pairs. Carbon, 1, 2, 3, 4 electron pairs, all bonding. Y, lone pair, 2 bonds. So everything has an octet that I'm interested in. This little markup here represents it's connected to some other molecule that I just don't care about for the time being. So I'm going to assume it's not involved in this particular resonance scenario. Okay, on the product, lone pair, pi bond, sigma bond. So 4 bonds. So it's set. Carbon still has 1, 2, 3, 4 bonds, just like before. It's set. Y has 1, 2, 3 lone pairs and a bond. So it is also set, meaning everything meets the octet rule. So according to our first stability rule, they're equal. They both meet octet criteria. Second one, you want to minimize number of charged sites. So generally speaking, plus reacts with minus. That's going to be the fundamental thought in organic chemistry and just chemistry in general. So if you have no charges, if it's neutral everywhere, then it's going to be less reactive. So consequently, if everything's neutral, it's a more stable condition than when you have charges. Because charges, now they're going to be more reactive. If a compound is reactive, that means it's less stable. So your stability means unreactive, unstable means highly reactive. And so charges make things reactive, so minimize charge sites. So based on this rule right here, that's our better structure. And then last but not least, occasionally you just have to have a charge. They just happen. You want the charges to be displaced in the best possible position, meaning negative charge should be found on more electronegative atoms, positive charge should be found on less electronegative atoms. The better you can do this, the better you can live with that charge, and the more stable the resonance structure. But based on these rules, we don't have to have charge sites. So that's why this rule takes precedence. You can have an uncharged resonance contributor, and you have this other one that is a minor contributor. So no idea exactly how much each one contributes, but we simply call this major and minor, meaning if I were to draw a resonance hybrid with a carbon, I'd have my bond to X, my bond to Y, and I would put a very small delta plus here and a very small delta minus, representing the fact that this is your major contributor, and you have a tiny amount where there's a positive here and a tiny amount there's negative there, and then you have a resonating pi system. Okay, so that's our fundamental rule. Octet, most important. Want to minimize charges if at all possible, and if you have to have a charge, put it where it is most comfortable. Okay, so not terribly challenging rules. And then also electron withdrawing and electron donating groups. Electron withdrawing, pull electron density away, make things more acidic and ultimately more electrophilic. Electron donating groups put electrons in, they make it electron rich, which makes it more basic and ultimately more nucleophilic. Okay, so we have these terms. I will go into more detail in future podcasts. So right now it's conversation. Soon it'll be practice questions and then come up on screen. Okay, for this, determine whether the following pairs of structures are resonant structures of one another or not. Okay, so to be a resonant structure, only electrons can move. You cannot move any atoms. So let's look at this, and this. They are all in the same spot. No atoms have moved. And this carbon in the middle and this oxygen are still in the same spot. So it's looking good. This carbon right here is also not moved. Perfect. But one of these H's, this one right here and up here, that H has changed location. So consequently, because we had an H and the pi bond both move. So this H right here was on this carbon, now it's on the O, pi bond moved over. So these are what's known as isomers. They are the same molecular formula, but different connectivity, which means you have atoms in different locations. They are not resonant structures. Okay, same test. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, all in the same spot. 6, 7, 8, all the atoms in the same spot. So it's looking promising. Now to figure out how this would happen. So the carbon went from a plus to having no charge, so it gained electrons from somewhere. Oxygen went from neutral to plus, so it had to lose electrons. Only way that is possible is if there's a lone pair that donates in. So let me clear what I just drew and draw that. Sure enough, no atoms moved. Pi electrons moved from a lone pair into a pi bond. So those are resonance structures. And just for point of interest, let's go back to the rules we just said. Does everything have an octet? So in this case, let me draw the lone pair that's still here. So H's we don't care about. This carbon has 4 bonds. This O has 2 bonds and 2 lone pairs. This carbon, though, is missing an octet. In the second structure, we have 4 bonds of carbon, so it's octet set. Oxygen, 3 bonds and 1 lone pair, octet set. So this one is octet stable. You're stuck with a charge. You can't get rid of it. So you have to have a charge. You want to minimize it. If possible, we can't minimize it. 1 charge is our minimum. And then finally, where does the positive want to be? We'd rather have the positive on the less electron atom carbon. So according to rule number 3, the left structure is better. According to rule number 1, octet, the right one's more stable. Octet takes precedence. So those rules were not just randomly aligned, they are aligned specific order. So top priority. So this is your major contributor. This is your minor contributor. However, unlike the previous case where it was the distinct winner on one side compared to the other, this one rule favors this, one rule favors that. So this will probably be a more abundant minor contributor, but still relative to the other structure, it will be minor. Okay, and finally, this last example, I'm going to draw my H's in. I have 1, 2 H's here, 1 H in the middle, and 1, 2, 3 H's here. Still have 1 H in the middle. Uh-oh, I'm down to 2 H's on this side instead of 3. And 3 instead of 2, so nope. And each had to move as drawn. So they're basically the same structure, flipped by 180 degrees, but you don't get to this by a pi bond relocating or electron density moving through a pi network. So this was the only one that was a resonance scenario. Okay, so starting to learn a few things. I can rank my resonance structures, which is going to become critical when looking at questions, which is the best structure? It'll be the one with the most resonance stability. This time, I'm going to go back to something we did in the previous example, but flip it around. So this structure maybe looked familiar because we went over this in the previous Toddcast, but that time we predicted like how to move the arrows. Now want to learn how to emphasize drawing the end result. So a lone pair that used to be on nitrogen is now gone and turned into a pi bond. So I'm going to start with nitrogen because that's where electron flow starts. And put a pi bond there and a plus charge. This carbon would get a 5th bond, so that bond is breaking. So this carbon is just fine. This pi bond has moved from between the 2 rings to now being firmly in just a 6-membered ring. So my pi bond is here. This then is going to have to force this bond up. So that's why we have 1, 2, 3, 4 bonds. That pi bond is broken. 2 lone pairs there, 2 lone pairs there, but this pi bond is turned into lone pair, and therefore a negative charge. So when we lose a lone pair, we have a residual plus charge. When we gain a lone pair or gain electrons, we have a residual minus charge. So these are the 2 charges you generated, and these are 2 possible resonance structures. There's other resonance structures, but I like to draw the terminating one, where the lone pair starts all the way up to where it ends. If you were drawing different resonance structures, because I drew 1, 2, 3 arrows, it's a reasonable guess that there are 3, 2 intermediate ones, and then this final one in terms of resonance structures. So if you are taking a class And I realize these are public videos, so there's a high probability that some of you watching these are not in my class. You may have an instructor that makes you draw each individual one. So in other words, they might make you draw this in here and put the charge stopping there. And the next one, the charge goes in there and that moves up there. And then the various intermediate structures. I like terminating structures because those are the ones that really matter most. Okay, I also want to take time to decide which one is more stable. 1, 2, 3, 4 in oxygen, all the carbons are set. 1, 2, 3, 4 in nitrogen, so everything's good. Nitrogen has 4, carbons are all set. Oxygen has 1, 2, 3, 4 with a bond. Octet rule satisfied. Rule number 2, you want to minimize charges? No, this one has no charge, this one has charges. So this will be my major. Ooh. This will be my minor. Okay, so we'll do another one. Again, this was a dipeptide we did in the last example, last Toddcast, talked about a resonance associated with a peptide linkage. Lone pair becoming a pi bond. I'm going to draw that in as such. And again, leaves a plus charge in its wake. The pi bond becoming lone pair ends up here and becomes a negative because that's where the charge finishes. Same question as before. Are octets all satisfied? Yes, yes. I'm not going to worry about the N ones. Yes, yes. Carbon set with 4 bonds in each case, so octet's fine, but charges, no charges. So once again, major and minor. Okay, so it's not bad, and you'll get used to it. It's recognizing where it applies is ultimately going to be the challenge with resonance. So last time we did a guanino group as well. So this, just for random information, is the side chain of arginine. This isn't the side chain of arginine, but the arginine side chain has this guanino group, so it is fairly common in bio. But just want to figure out where everything goes. So this nitrogen is going untouched. So we're only looking at one of the resonance structures possible. So we have a plus charge and a pi bonds moving towards it. If electrons moving towards it, then you're going to get rid of the positive charge. So in the end, this nitrogen is going to have its lone pair, and it's going to be neutral. And this nitrogen, which had a lone pair that's donating in, that's now going to form the pi bond and leaves behind a plus charge in its wake. Okay, this will be a more challenging one to figure out what the major contributor is in this case. So in this situation, that one's fine. Octet is maintained. Carbon in the middle, 4 bonds in each case. Nitrogen here has 4 bonds. Here it has a lone pair and 3 bonds, so octet. This one has 2 H's, so 2 bonds plus a bond to carbon, 3 bonds and a lone pair set. 2 bonds and 2 bonds H, so 4. Everything's octet. Okay, it has a charge, so we're stuck with it. We can't minimize the charges. Plus is there. And then the last one, put it where it can best be facilitated. So this is an interesting scenario where we have nitrogen, nitrogen. So at face value, our initial thought should be they're one and the same. But they're not exactly identical. This nitrogen is interior. This one is terminal, meaning it's at the end and it's a primary. It only has one other atom attached. This nitrogen has 2 other carbons, and this only has 1 carbon. I should say just atom, but carbon specifically. So secondary, as it stands, ends up secondary amines. We're going to learn this many chapters down the road, but secondary amines, because of the donating group of the R groups, the carbons can donate in, make a little electron richer, makes it more basic. If it's more basic, it is better able to give away its electron density. So this one can give away electron density better than this nitrogen, meaning this left structure will be ever so more stable because it's more basic, so it's better able to give away electron pairs and take on that plus charge because of the donating groups, the inductive effect, as we'll learn on that side. This, if you really had to decide, would be major, minor. Reality is no teacher is probably going to make you distinguish between those two Just off the top of your head, they might say that in a certain hydrogen bond that forms in a biomolecule, we find that one nitrogen is more commonly involved than the other. How would you explain it? And then you could say, because of inductive effect, this would be a better donor. Or you might say, because of resonance features, because this is a slightly better resonance structure, plus charge here is stabilized. So this is going to be the one that the negative charge will be found closest to. Whatever the question may be, real fine line difference. So this is a more challenging question. Okay, starting with the middle structure below, which only one structure is shown, so it'll make sense where we're going to get after this. This is a case where we have to put in lone pairs. Function has 1, 2 lone pairs. Everything else is carbon and hydrogen, so no lone pairs to worry about. You have a positive charge here. You want to get rid of that positive charge, so you know the pi bond is going to pull this way. I'm going to draw this one, and I want you to tell me what I'm doing wrong when I do this. So if I push this in, keeping in mind there's an H there, that's a fifth bond. So it would have to move over to there. Now I made a fifth bond to nitrogen. So if I push that away, I now have made 1, 2, 3, 4 bonds and a lone pair and oxygen. So the resonance cannot push in this direction. You violate the octet rule. So with that in mind, there's only one way resonance can go in the structure. You can only donate lone pair in that way, pi bond out that way. Okay, so we're going to share that charge. So intermediate structures along the way. I'm going to draw this structure to tell you then that this pi bond is still here. This is now forming a pi bond with just one lone pair and a positive charge. And this has now become a lone pair. So that's one resonance structure. But now the question is asking for a second one. So this is a case where, from my perspective, drawing the intermediate one is sort of silly, but I'm still going to do it. If we just were to consider just this part, that one breaking, so I'm going to draw it in a way where this is this resonance. If we just drew that one, then we would have pi bond here. We now put a lone pair there. We retain our 2 lone pairs here. But now we've created a positive charge on that carbon. So this positive charge on the carbon in non-octet, the reason I sort of blow by it is because it is such a minor contributor because it doesn't have an octet that I don't know if it's worth drawing. But if you're in a class where you have to draw all the possible resonance structures, then sure enough, there are 2. One arrow breaking would get this one, and then the other arrow coming in would get the final one. Okay, let's keep playing. So now we have a negative charge. We have to facilitate, move it around. So lone pairs can become pi bonds, can move to the right, or can move to the left. So I'm going to do it first to the left towards the oxygen. So I'll do that in purple. Shoot, my thing shifted, my apologies. When it comes in, that'd be a fifth bond to carbon, so you can't do that. You got to keep going. It'd be up there. So let me go ahead and put my lone pairs in this O. So now I have this lone pair up here. And we've created a pi bond right here to that carbon. That has a negative charge. To be complete, let me go ahead and put my lone pair also on sulfur. So we have one resonance structure. That's when it resonates to the left or to the oxygen side. Okay. On the other side then, I'll do that in different color. Had the lone pair gone from here to there, that pi bond would form. That's 5 bonds of carbon, so that must break. That lone pairs will go up there, and you will end up with this resonance structure. So O retains its 2 and sulfur, which originally had 2, But now the pi bond between carbon and carbon exists, and a lone pair is now formed on sulfur, and the negative charge is there. So we have three resonance structures, and now kind of a fun thing to do. Okay, there's an H that has been written in here, here, here. So I'm going to put it in green to say there's an H. So now to the octet analysis, 4 and 1 bond, 4 bonds, 2 and 2, octet completely satisfied, octet satisfied, 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 octet satisfied all the way around. Charge, we got to live with it. There's negative charge, there's one charge in every single structure, can't get rid of it. So second rule. So finally, the rule, put it where it's most stable. Fonk O Brish. I'm a big fan of this. So O is number 1, so that's my number 1 contributor. S is number 2, and carbon is number 3. If we go by a simple model of more electronegative atom can stabilize it most readily, that'll be perfect. If you get into more advanced organic chemistry, we'll start looking at the fact that a bond between a 2p and a 2p pi bond, as opposed to 2p and 3p, also has some issues, some impact. At the level of first semester organic chemistry, probably going to ignore that feature. So just based on simple stability of where you want that charge, number 1 on O, number 2 on S, number 3 on C. So the big things to walk away from this particular Toddcast, make sure you can identify that pi bonds are contributors in the electron withdrawing groups. Electron density pulls away, pi bonds break. Know that lone pairs are electron donating groups, so that you'll find them in I don't know, electron donors. This will impact reactivity. We'll get into that down the road, and then definitely know how to identify the more stable and less stable resonance structures. So octet first, minimizing charges second, and put charge where it can be best held third. Rule number 1, if they're all equal, then go to rule 2. If that's all equal, then go to rule 3. So hopefully this was a educational one. So I'm going to stop recording, and I will see you at the next Toddcast. Bye.